Welcome to another episode of our series on quantum physics. In this video, we will explore the fascinating topic of quantum field theory. While quantum mechanics describes the behavior of particles at the subatomic level, quantum field theory takes it one step further by treating particles as excitations of underlying fields. This theory provides a framework for understanding the behavior of particles in a way that is consistent with both quantum mechanics and special relativity. So let's dive in and unravel the mysteries of quantum field theory. What is quantum field theory? Quantum field theory is a framework for understanding the fundamental laws of nature. It is a theory of quantum particles and their interactions, as well as a description of how these particles move through space-time in the presence of gravity. The theory was created by Werner Heisenberg, Pascal Jordan, and Richard Feynman at Cornell University in the 1940s. Quantum field theory can be applied to all types of matter: atoms, molecules, solids, and even black holes. What do particles and fields have to do with it? Quantum physics is all about particles and fields. Particles are the fundamental building blocks of matter, and the electromagnetic field is a force field that produces the electric and magnetic forces. A particle is a localized region of an energy field. It's made up of everything from electrons to quarks, but doesn't have any mass or size itself. In other words, it's not something like an apple falling off your desk. Instead, think of them as points in space filled with incredibly high energies. You could say they're pointy because they're so high in energy. The reason why quantum physics matters so much today, because we live in a world where everything has been explained by particles. Matter, including us, light waves such as those produced by lasers, even time itself can be explained through this theory. How are Feynman diagrams used in calculating properties of particle interactions? Feynman diagrams are used to calculate the probability of an event occurring. For example, if you have a particle interacting with another particle, you can use Feynman diagrams to construct a series of events that describe how these particles interact. You then measure which outcome occurs and calculate its probability by analyzing which path is most likely. Feynman diagrams are very useful in quantum field theory because they allow physicists to visualize interactions between particles quickly and easily without having to go through complicated calculations or derive formulas for each step along the way, which would take too much time. By breaking down complex phenomena into simpler parts like this one does on paper before taking them apart again later, when needed, after more careful thought, we get closer than ever before. We get closer than ever before understanding what's really going on. What is an expectation value, and why does it matter in quantum mechanics? In quantum field theory, interactions between particles are described by the exchange of photons. The photon is a particle that has zero rest mass and can travel at the speed of light. It's an essential part of our lives, but it also makes up part of the second law of thermodynamics. Energy can neither be created nor destroyed in isolation. When you heat up something like water, it loses kinetic energy until it reaches its absolute temperature. In quantum mechanics, we have a similar situation. Quantum fields exist everywhere at once in space and time. If you had enough information about those fields before they were measured, then measuring them would tell you everything about them. What does it mean for a theory to be renormalizable? Renormalizability is a property of a theory. A theory that is not renormalizable cannot be used to make predictions about physical phenomena, because the theory does not describe the behavior of systems in nature. When we say that a theory is renormalizable, it means that there are ways to make corrections from experimental data and still have your theory work out just fine. This allows you to use your predictions for new experiments or situations. Even if those predictions are not always exactly right, they'll be close enough so that people can still get useful information out of them. Predicting what kind of material will conduct electricity. How does the Higgs boson fit into this picture? The Higgs boson is a particle that interacts with other particles to give them mass. It was discovered at CERN in 2012 and it's part of the standard model of particle physics, the theory that describes how elementary particles work. The standard model has been tested against observations, but it still isn't completely confirmed by experimental data. For example, there are some questions about how the Higgs boson behaves under extreme conditions, such as high temperatures and pressure, or when it is close to other particles. See, is there a Higgs particles? See, is there a Higgs particle? Other theories exist beyond this one which could explain these anomalies, but until they're tested against experiments like those performed at CERN or Fermilab, we can't be sure which one best explains what we see happening in our world every day. This is how QOFT relates to other areas of physics. Quantum field theory is the foundation of many other areas of physics. The main example is particle theory, which studies how particles interact with each other and their surroundings. QOFT also provides a way to calculate properties of the Higgs boson, which explains why it has mass in the standard model. In addition to being used by physicists, QOFT has applications outside of academia as well. Companies like Google and Facebook use quantum computing to solve problems that would take normal computers millions or even billions of years to solve. Quantum field theory is one of the most remarkable developments in modern physics. It has revolutionized our understanding of how matter behaves at the smallest scales and how subatomic particles interact with each other. The Higgs boson was discovered in 2012 as a key component of this theory and has provided us with new insights into how nature works on the subatomic level. As we conclude our exploration of quantum field theory, we have gained a deeper understanding of the fundamental nature of the universe and the underlying principles that govern it. From the study of subatomic particles to the behavior of fields, this branch of physics provides us with a powerful framework to investigate the intricacies of the quantum world. While there is still much more to uncover, we can be certain that the insights we gain from quantum field theory will continue to shape our understanding of the universe and inspire us to continue pushing the boundaries of science. Thank you for joining me in this journey, and I hope that this video has left you with a sense of wonder and curiosity about the mysteries of the quantum world.
What?